Okay, so Justin Thaler is received his PhD from Harvard Computer Science School in the area of streaming and sketching models. But by the way, Justin, if I'm inaccurate, just feel free to jump in. He's an associate professor at Georgetown University, author of the book Proofs, Arguments, and Zero Knowledge that we're using constantly, a member of the Andreessen Horowitz A16Z crypto research team. He's made fundamental contributions to many areas of CS, and he's one of the leading researchers in the ZK community. I met Justin recently at the ZK Proof conference. I asked him to come speak to us, and he agreed. The topic of today's talk is a deep dive into the Sumcheck protocol. Without further ado, I hand over to Justin. Thank you for coming.
Yeah, no, thanks so much for having me. Yeah, looking forward to getting to know all of you more. It was great talking to you all at ZK Proof, and yeah. So I'll just share my slides here. Oh, great. Okay. All right. Okay. Yeah. So please interrupt. I know that at least some of you have to take a moment to unmute to interrupt. So please just do that. And yeah, so I'm going to present the Sumcheck protocol, and which is actually an interactive proof. So it doesn't use any cryptography. And I'll sort of indicate how you can get snarks, which do use cryptography, by kind of combining the Sumcheck protocol with cryptographic protocols. There'll be more information about that in a couple weeks. I'm giving a lecture at a MOOC. So I try to make these the presentation I'm preparing for that and today's presentation complementary. So if anyone is interested in sort of both talks, they should kind of be additive to each other. Okay, so yeah, I'm going to briefly tell you what is an interactive proof and introduce a couple of important technical concepts, which many of you have probably seen before, like the short-zip lemma. Then we'll dive into the Sumcheck protocol and see a couple examples of how you can kind of use the protocol as a hammer to solve a bunch of problems where it might not be immediately obvious that they're amenable. Yeah, and then we'll just see how time goes. Okay, so in an interactive proof, I think a nice application to have in mind when you're thinking about the model is, there's some computationally limited verifier that is outsourcing some computation, let's say, to a commercial cloud computing service, because it's just too heavy a computation for the computationally weak verifier to do on its own. So the verifier or user might send a bunch of data up to the cloud. The cloud will store the whole data set. It turns out the user can typically just store a very small summary of the data. So it can actually forget most of the input to the computation, just keep a very small summary of it. And then later, the user can decide what analysis it actually wants to do of the data, and ask the cloud to run that analysis on its data that the cloud has stored. Typically, that question we imagine might be in the form of a computer program that the user is asking the cloud to run on its data. And the cloud comes back and says, I ran your program on your data, and here's the output. But the user doesn't trust that the output is correct. So it starts interrogating the cloud, sending a sequence of challenges and getting a sequence of responses, at the end of which it has to decide whether to accept the cloud's answer as valid or reject it as invalid. Okay, so we require standard completeness and soundness properties, which I assume most you're all familiar with. But completeness just says that if the cloud is honest and returns the correct answer and follows the protocol, the verifier will accept. And soundness says if the returned answer is incorrect, then no matter what the cloud does to try to convince the verifier to accept, it won't succeed except with tiny probability. And for interactive proofs, again, there's no cryptography. So the soundness property for interactive proofs actually has to hold against a computationally unbounded prover trying to trick the verifier into accepting. Now, what people tend to be interested in today is not interactive proofs, but snarks, which is, again, something I expect, probably all of you know, but just as a brief reminder, in a snark, the prover claims to know a witness satisfying some property. And the example I like to give in, like in the MOOC or, people who are encountering snarks maybe for the first time is, the prover claims to know like a pre-image under a cryptographic hash function of some particular hash value. So, the verifier knows the hash function and the hash value, but doesn't know the pre-image, and the prover's claiming to know the pre-image. And like the trivial proof of knowledge of this pre-image W is to just send W to the verifier, who can then just evaluate the hash function on W and confirm it has the claimed output. So a snark is just a cryptographic protocol that achieves the same property, but with better cost to the verifier. So the S in snark stands for succinct, which basically means that the proof should be shorter than the proof in the trivial proof, consisting of the entire witness W. And ideally, checking the snark proof will be faster than the verifier, taking explicitly the witness W as input and checking the witness W itself. So there's some variance in what people mean by succinct, but I use succinct to mean like as long as the proof is strictly shorter than the trivial proof W, I say it's succinct. And to talk about the verifier runtime, I use the term work saving. So if the verifier of the snark is faster than what it would take to just check the witness W directly, I use the word work saving rather than succinct to be very precise about runtime versus proof length. Does anyone want to ask a question at this point? Okay, yeah, so I probably this is our review. I'll try to move through it fairly quickly. How do you get a snark from an interactive proof? So I'm not going to go into a huge amount of detail about this, but I can give an indication certainly. So again, in the trivial proof system, where you don't use an interactive proof, you don't use any cryptography, the trivial proof system is the prover just sends the witness to the verifier, who just directly checks it for validity, right? Now, an interactive proof on its own cannot give you succinctness, but can give you work saving, right? So without using any cryptography, you can get a work saving verifier. The idea is the prover still sends the full witness to the verifier, which is why the proof is not succinct. But then rather than the verifier directly checking that the witness satisfies the claim property, the prover can prove to the verifier that it satisfies the claim property, thereby saving the verifier the time of checking the witness. So this will give you a work-saving protocol, but not succinct. And then to get a succinct protocol, what happens essentially is rather than sending the whole witness to the verifier, the prover cryptographically commits to the witness. And this commitment will typically just be like a single cryptographic hash value or a single cryptographic group element. And then you run like the interactive proof, whereby, the prover's kind of pretending like the verifier does have the whole witness now, even though it doesn't, it just has a commitment to the witness. And then at the very end of the protocol, the prover uses you need a commitment scheme that allows the prover to reveal just enough information about the witness inside the commitment to let the verifier run its checks in the interactive proof. So you're kind of using cryptography to simulate the prover having sent the whole witness to the verifier without the prover ever having to actually send the whole witness to the verifier. So that's how you get succinctness and not just work saving. And it's an interactive proof, so it sounds like it's still not a snark because it's not non-interactive, but typically these interactive proofs will be public coins, so you can just make them non-interactive with fiat shamir. So that's, again, throwing more cryptography on top of the interactive proof to, give it nice properties required by snark. Okay, so that's how you get snarks from interactive proofs. This commitment in general is, what it winds up using is something called a polynomial commitment scheme, which I might say more about that later in the talk, but I won't get into the details of that at the moment. Okay, so that's most of the intro about models and definitions. So let me just see if anyone wants to ask anything. Otherwise, I'll carry on. Cool. Okay. So let me start talking about like how interactive proofs actually work in their guts. So the actual technical notions they utilize. So I'll start with something, again, you're probably all familiar with, which is the short Zippel lemma. So for univariate polynomials, this is just the simple statement that any two distinct degree D polynomials can agree on at most D minus 1 points. So another way of saying that is if you know, the verifier or, you know, some randomized algorithm just picks a random input in the whole field that the polynomial is defined over and evaluates 2 degree D polynomials at that point, then if they're not the same polynomial, the probability they wind up agreeing at that randomly chosen input is at most the degree over the field size. Okay, so this is, I don't know, the fundamental theorem of algebra, or I even forget, it might even be simpler than that. I forget in 8th grade what we call this. And the short zipple lemma is just a generalization of this from univariate to multivariate polynomials. So short zipple says if P and Q now are L variate polynomials where L can be, you know, much more than 1 potentially, and their total degree is at most D, then the same property holds. So if you evaluate the 2 polynomials at the same randomly chosen point, if they're not the same polynomial, they'll sort of they'll agree at that input only with probability like degree over field size. And here total degree means like you look at every monomial in the polynomial and you sum up the degrees of each variable in that monomial. So in this little example on the slide, the total degree is 3 because like the highest degree monomial has degree 2 in variable 1 and degree 1 in variable 2. So 2 plus 1 is 3. Okay, so now we get to a notion that might be a little newer, which is the notion of low degree extension polynomials, particularly multilinear extension polynomials. So these are the kinds of polynomials that the interactive proofs I want to tell you about today like use in their guts. So imagine we have a function f whose domain is like the L-dimensional Boolean hypercube, right? So the domain of f is just length L bit vector, 0, 1 to the L. Okay, and we're going to wind up interpreting like 0 and 1 as field elements. So every field has, you know, an additive and a multiplicative identity, 0 and 1. And we're thinking of f as taking as input like only length L vectors of 0, 1. Yeah, so the domain of f itself is just 0, 1 to the L, but if we have an L variate polynomial G, which is defined over the entire field, we say that G extends f if evaluating G at a Boolean input gives you the same thing as evaluating f at that input. Okay, so I'll make this more precise with the picture in a moment. But what's happening here is you think of like the domain of f is fairly small. It's just 0, 1 to the L. But the domain of the polynomial G is field to the L. So G has a much bigger domain of f, much bigger domain than f. But G is said to extend f if when you do evaluate G at any input where f is defined, you get out the same thing as if you evaluate f at that input. Okay. So I think of these L variate, you know, extension polynomials as like kind of extending the domain of G to a much bigger domain, from 0, 1 to the L to field to the L. And it turns out it's not too hard to show using Lagrange interpolation that if you give me any function whose domain is, you know, 0, 1 to the L, there's a unique extension polynomial that's multilinear. So multilinear means it has degree 1 in each variable. Let me see. Okay, so yeah, so here's a simple example of a multilinear polynomial. But like if as soon as you have a variable appearing with degree 2, your polynomial is not multilinear. So any function f whose domain is 0, 1 to the L has many extension polynomials, but only exactly one of them will be multilinear. We'll have degree at most 1 in each variable. So pictorially, this is what multilinear extensions look like. So here's a function f defined on you know, like 2-bit inputs. So 0, 1, you know, squared. So for each of those 4 inputs, it spits out some field element. So like this is f of 0, 0, f of 0, 1 is 2, f of 1, 0 is 8, f of 1, 1 is 10. And here is its multilinear extension. So, you know, whereas f itself had domain of size 4, the multilinear extension polynomial is defined over, all pairs of field elements, right? And like often when we run these interactive proofs, the field size is say 2 to the 128 or 2 to the 64 or what have you. So, vastly, vastly bigger domain size for the multilinear extension polynomial relative to f itself. It's the difference between like 2 to the number of variables versus, field size to the number of variables. Okay. Yeah, so I guess you're probably all familiar with Lagrange interpolation, but here's kind of Lagrange interpolation in one slide. So if f has these 4 inputs 0, 0, 0, 1, 1, 0, 1, 1, we can express f twiddle, the multilinear extension, via Lagrange interpolation, where you kind of sum over each of the 4 inputs to f, and ensure that the polynomial you're defining, f twiddle, has exactly the correct behavior on that input. So for example, if f of 0, 0 is 1, this is like the Lagrange basis polynomial that captures that, right? So 1 minus x1 times 1 minus x2 will map 0, 0 to 1, and any other bit vector to 0, right? Because if even one of x1 or x2 is 1 rather than 0, you get a factor of 0 and it kills this term. So this term ensures that the polynomial we're defining has exactly the right behavior at the input 0, 0, and like doesn't, and evaluates to 0 at all of the other Boolean valued inputs. And similarly, this term here has exactly the right behavior at 0, 1, so it maps 0, 1 to 2, and make sure to kill all other bit vectors that you feed into it. So you can define the multilinear extension f twiddle by going input by input over f, so summing over the Boolean hypercube, and for each one defining a polynomial that sort of picks out just that input and does the right thing on that input. So yeah, there are other extensions of f. So here's another extension polynomial of f. So this is a quadratic extension. It has total degree 2, and it has the same behavior as f on the Boolean inputs. 0, 0, 0, 1, 1, 0, and 1, 1. But it's not multilinear. So yeah, to summarize everything that I said, you give me any function f whose domain is 0, 1 to the L. There's a unique multilinear polynomial that extends that function to like the whole field. And there are many other extensions as well, but only one of them is multilinear. I think conceptually the way to think about these extension polynomials is as an error corrected or at least distance amplifying encoding of f. And in fact, it has a name called the Reed-Muller code. And the key point is that if 2 functions defined on the Boolean hypercube 0, 1 to the L differ at even a single input, their extension polynomials disagree at almost all inputs. And that's just the Schwarzschild lemma, which says if you take 2 low-degree polynomials and they're not the same polynomial, they disagree almost everywhere. Okay, any questions? Okay. Yeah, so a key fact about these low-degree extension polynomials and multilinear ones in particular, because the prover and the verifier in our interactive proofs are going to have to evaluate these extension polynomials at a small number of inputs. So it's really important that that one be able to do that quickly. So a key fact is if I give you like a list of all 2 to the L evaluations of a function f defined over 0, 1 to the L. And I also give as input to the algorithm a point r in the field. So it's not in 0, 1 to the L, it's in field to the L. And you want to evaluate the multilinear extension polynomial of f at r. You can do that in linear time. So again, linear means linear in the size of the input to the algorithm. And here the input to the algorithm has size 2 to the L because it's just a list of all evaluations of F. And there are 2 to the L inputs to F. So that list has length 2 to the L. So I won't explain exactly how that works, but it uses simple dynamic programming memoization. Without dynamic programming, you wind up with an extra, you don't get 2 to the L time, you get L times 2 to the L time. But anyway. Any questions about this fact? Okay, so with that, like really dry technical preliminaries out of the way, we can finally talk about the Sumcheck protocol. And the connection between, the Sumcheck protocol and like multilinear extensions is not going to be made clear until we try to apply the Sumcheck protocol. So when I present the Sumcheck protocol, it's still going to be like kind of fairly abstract and not clear why this protocol would necessarily be useful. But as soon as I cover the Sumcheck protocol, we'll immediately start seeing how to apply it, and then that will become much more concrete and clear, like why this thing is actually useful and how it connects to multilinear extension polynomials. Okay, so this protocol dates all the way back to like very early work on interactive proofs. So late 80s, early 90s. Lund, Fortnow, Karloff, and Nissan. And kind of once you know this protocol, you start seeing its applicability kind of everywhere you look. But here's how to think about the protocol as a standalone object. So it's easiest to describe if you imagine that the verifier, so this like computationally limited verifier that's trying to check a claim by an untrusted prover, is given like oracle access to an L-variate polynomial G. Okay, so that's why this description is abstract. Is it's a little hard to tell you like what this polynomial G will be in applications until I actually I'm able to show you an application. So right now though, just imagine that there's this box in the sky, and the verifier can go to the box and say hey, tell me G of R for like a point R chosen by the verifier, and the box will come back and say here's G of R, and like the verifier can trust that box. So, the verifier potentially doesn't even know what G is. It doesn't have a complete description of this polynomial G. But if it goes to the box and says, hey, box, tell me G of R, the box will come back and truthfully tell it G of R. Okay, so that's kind of the power given to the verifier in this protocol, is to evaluate this polynomial G at a single point. But what the verifier really wants to know is not G's value at a single point, but rather the sum of G's evaluations at 2 to the L points, namely all Boolean inputs 0, 1 to the L. Okay, so the verifier could solve this problem on its own by like asking the box 2 to the L questions and just summing up the answers. But we're considering that like way more expensive than we want the verifier to actually spend time doing. So we're going to kind of outsource the hard work of evaluating G at these 2 to the L points to the prover. And the verifier is going to wind up just evaluating G at a single point by asking the box one question. So from the verifier's perspective, the Sumcheck protocol is a reduction from summing up G's values over the Boolean hypercube to evaluating G at just a single, turns out it'll be randomly chosen point. Okay, does the setup make sense? Cool. Okay, someone might want to, because since I don't have, I only have my slides up, so someone might want to say something at some point just so I know I'm still on the call. But anyway, okay. So yeah, let me describe. Oh, yeah.
Yeah. So like, could you also just maybe give us a like what kind of questions like in the NP class can like reduce to a Sumcheck problem? Like when?
Yeah, sorry. So the question is like, what will the Sumcheck protocol be useful for solving in the end?
Yeah, like when, like I know that like for example, when you want to say in an R1 CS equation, you have a matrix multiplying by a vector, and you want to check that I know the value that I used to correctly multiply the matrix, then I can reduce this to a Sumcheck problem.
Yeah.
So in general, it's maybe just a general question, like when are the situations, for example, I can reduce it to a Sumcheck problem? For example, if I have a computational integrity check, can I reduce it to a Sumcheck problem?
Yeah. So Yeah, it's a slightly hard question to answer in a succinct way, which is why I have some example applications to show what it's useful for. But I can say a little bit now, I guess. So like you mentioned, the Sumcheck, there are like snarks for R1CS or circuit satisfiability or what have you based on the Sumcheck protocol. And in that case, what happens is the prover kind of winds up cryptographically committing to the multilinear extension of like a witness to the R1CS instance or the circuit sat instance. And then for one derives a polynomial G, which sums to 0 over the Boolean hypercube, if and only if the witness is valid. Okay, so there's a lot of magic in that reduction and like kind of identifying, going from the witness to a polynomial that sums to 0 if and only if the witness is valid. And that's actually the main focus of the lecture I'm going to give at this MOOC in a couple weeks. So I can't really go into much detail about how that works, but that's why the Sumcheck protocol is so useful for snark design. We will see some examples like right after I describe the protocol where, I'm going to describe some problems like matrix multiplication and counting triangles in a graph where you'll just see like the problem, with a little creativity is you can identify a polynomial G so that summing up the evaluations of that polynomial will just give you the right answer. And with all of these applications, the key is that the verifier in the end does have to evaluate G on its own at one point, right? Like the verifier is not really given a box in the sky that it can ask for the evaluation of. So a lot of the cleverness here is showing that the verifier on its own can very efficiently evaluate G at a single point. And that's enough to force the prover to do the hard work of evaluating G at the 2 to the L points at which it needs to be summed. So I don't know how useful that rambling was, but maybe I should have just said if you could just wait till the applications and that'll I think make things more concrete. Any other questions?
Kartik, we can't hear you. I think you were talking, right?
Yeah, thank you. It's good.
We're fine. Yeah, thank you.
Okay, great. All right. Any other questions?
I'm going to keep this unmuted, so if there is an echo, tell us and we'll mute. But
sounds good. Seems okay, I think. Okay, I'll continue. Okay, so yeah, so again, the prover is going to do the hard work of summing up G's evaluations over the 2 to the L Boolean inputs and prove to the verifier that it's done it correctly. Okay, so at the start of the protocol, the prover just sends the claimed answer to the verifier, and the verifier has to check is the claimed answer like what it should be. So to start that proof, the prover sends a univariate polynomial, which is claimed to be the following thing. So what we've done here is we're still summing over the Boolean values to all but the first variable. So we're still summing over variables 2 up to L, but we're leaving the first variable kind of unbound or free. And in that way, we kind of take this L-variate polynomial G and turn it into a univariate polynomial because, we're leaving the first variable unbound, but, summing over the last L-1 variables. Okay, so let's call, so the prover sends this polynomial S1 in a single variable, and that the prover's honest, S1 equals this other thing, H1. Okay, but the verifier doesn't know if the prover's honest, of course, so it has to do some randomized checking to try to detect a lie. So what the verifier does is it picks a random point Okay, sorry. It does two things. So first, it has to check that, like, assuming the prover is honest and S1 equals H1, the verifier needs to check that is consistent with the true answer to the whole problem being C1. So it does that check. So, you know, if the prover is honest, then C1 will equal S1 of 0 plus S1 of 1, right? Just sort of by definition here, you know, the full sum is obtained from this partial sum by, you know, setting the first variable to 0 and to 1 and summing the results, right? Because the full sum just is you get the partial sum from the full sum by, like, cutting out the sum over the first variable of being equal to 0 or 1. Yeah, so the verifier's first check says kind of like, well, let's for a moment assume that S1 does equal H1 like it should, and let's check, you know, is that consistent with the original claim of the full answer being C1. Okay. Yeah, assuming that that check passes, the verifier needs to try to check, like, does F1 equal H1? And it does that by just picking a random point and evaluating. You think of the verifier as looking to evaluate S1 and H1 just at that random point, right? And this, like, the univariate Schwartz-Zippel lemma tells you that if S1 does not equal H1, right, then with overwhelming probability, they'll actually differ from each other at this random point. Okay. So what happens is, yeah, the verifier picks this random point. Let me call it R1. And it needs to check, does S1 of R1 equal H1 of R1? And because the prover, like, sent it S1 directly, you know, we defined S1 to be the univariate polynomial the prover actually sent to the verifier. It can just compute S1 of R1, like, on its own in constant time. Think of G as having degree, like, 2 in each variable. So, you know, when the prover sends S1 to the verifier, it just sends, like, 3 coefficients to the verifier. And, you know, the verifier can evaluate this quadratic polynomial at any point in, like, you know, with, I don't know, 3 multiplications or something. So the problem here, the reason we're not just done, is that the verifier doesn't actually know what H1 is, because H1 itself still involves a sum over, you know, 2 to the L-1 terms. Yeah, the verifier has to check, does S1 of R1 equal H1 of R1, but it doesn't actually know what H1 of R1 is. So what it does is it just sort of recurses, right? So the value H1 of R1 is of the, you know, it's defined as a sum over, you know, the L-1 dimensional Boolean hypercube of G, but with the first variable fixed to R1, right? And that's just the same, it's the same form that we applied the Sumcheck protocol to solve originally. It's just with one fewer variable now. So rather than having L variables we're summing over, we only have L-1, right? So they just recursively invoke the Sumcheck protocol again to check that, you know, this sum here over L-1 variables has the value that, you know, it should have if the prover is being honest. Okay, so that's it. So they just go round by round, variable by variable through the variables of G. In each round, like, a new variable kind of gets fixed to a random field element. Yeah, well, you keep doing this, and eventually you wind up fixing every single field element, every single variable to a random field element. And once you do that, you don't have to kind of recurse anymore, because, you know, in that final round, the Lth, you know, round, you know, the prover winds up claiming that, you know, G at a fully specified input R1 to RL has a certain value, and at that point the verifier can just go to the box in the sky and ask for the evaluation of G at that point. Okay, so that's the whole protocol. And you know, I've kind of indicated via the description that it's complete and sound, right? So, like, it should be clear that if the prover is honest and actually sends the prescribed protocol in each polynomial in each round, like, everything is defined so that the verifier's final check will pass. You know, when it goes to actually evaluate G at a random point, you know, the value that the prover claims that point should have, it will actually have. That's almost just by how we defined these messages through the whole protocol. And then the soundness proof works as I sort of sketched, which is, if the claimed answer C1 at the very start is wrong, okay, then with overwhelming probability over the choice of R1 in the first round, S1 of R1 will not equal H1 of R1, because the prover will have to send a polynomial S1 in the first round that deviates from what it should be H1. Just otherwise, you wouldn't get consistency with the claimed answer if the claimed answer is a lie. So you go the soundness analysis. You just sort of look at each round of the protocol and say, well, in each and every round, unless the prover gets really lucky with the choice of field element chosen in that round, and SI and HI happen to agree at that one random point, despite being different polynomials, the prover will be left with a false claim to prove at each round, and in particular, the final claim will still be false, and then if that final claim that SL of RL equals G of R1 to RL is false, then with overwhelming probability if that final claim is false, then when the verifier goes to evaluate G at a random point, which it does correctly, it'll reject. That final check will fail. So kind of with overwhelming probability, unless the prover gets lucky in one of the rounds, it's left to prove a false claim in every single round, and then when it finally gets to the end of the protocol, it's out of room to try to get lucky. It's going to fail at that point, because it claims G should have some value at this input, and it just doesn't. G just does not have the claim value at that input, and the verifier evaluates G sort of in a on its own, or by asking this trusted box at that input, and will reject. Okay, so that's completeness and soundness of the protocol. So let's briefly talk about its cost, and then I want to get to the applications. Yeah, please.
Regarding the soundness, what kind of can I do malleability, like add some constants and so on and so forth, that it would still fail the final step? Like if I add to S1, S2 arbitrary constants such that I pick the result.
Yes, yeah. So the soundness guarantee, holds even against computationally unbounded provers that can, try to take two polynomials that had already sent or something and munch them together. It doesn't matter what the prover does. It's just, if the prover does not send the prescribed message in every single round, the verifier will reject, except with probability. It turns out number of variables times degree in each variable over field size. And in practice, think of this at, L might be 30 or something, and D might be 2. And so this is like 60 over, 2 to the 128 or something. And it literally doesn't, if the prover doesn't do exactly what it should do in every single round, the verifier is going to reject, except with that probability.
And is this the same argument for small fields? If I choose 62-bit fields or something like that, then
yeah. So it is the same argument. It's just that probability that a cheating prover kind of gets lucky and passes the checks despite lying, just won't be. If your field has size 2 to the 32, that probability will be something like 60 over 2 to the 32. Which is, small, but not cryptographically small. So what you'd have to do some kind of repetition to drive the soundness error lower in that case. Does that make sense?
Yeah.
So are the stages statistically independent, or is this a union bound?
It's just a union bound. Yeah.
Right. Another question. I don't know if you touched this, and maybe we should just. But what's that G oracle like? Can you say 2 words about that?
Yeah. So we will see this in applications. It'll be clearer, what that G oracle is. But the short version is in snarks, right? The prover will commit to the multilinear extension polynomial of like a claimed witness. And the G polynomial, the verifier needs to evaluate the G polynomial at a random point, and it'll be possible so in order to evaluate G at a random point, it'll be sufficient for the verifier to evaluate the committed polynomial at a random point. So yeah, this is very abstract, but there's, G is defined in terms of the witness polynomial in some way, such that evaluating G at a random point is like equivalent to evaluating the committed polynomial at a random point. I won't talk about, like committed polynomials in this talk, because I don't want to go into the cryptography, but I will cover an application where you'll see in that case, the G polynomial, it will be, the verifier will just be able to evaluate the G polynomial on its own, like very quickly. You'll see that very concretely shortly.
At any random point or at a setup point?
No, any random point. It doesn't any point, so it doesn't have to be random. So, and
Right.
that winds up invoking. Okay, so in the setting where the polynomial is, committed cryptographically, the verifier kind of gets that commitment scheme actually more or less acts like that box in the sky. But in settings like where the polynomial it does not involve a commitment, but is just like derived from the input to the verifier in some way. Like what I'm invoking, let me just go back to it. Apologies for, is this. So the input handed to the verifier, and again, we'll see an example of this in a minute, will wind up specifying all 2 to the L evaluations of some function, and the polynomial G will be derived from a multilinear extension of that function. And we have this algorithm that is able to efficiently evaluate multilinear extensions at any desired input quickly. And this shouldn't be like super mysterious. Like in the case of univariate low degree extensions, which is maybe more familiar to people who haven't come from studying interactive proofs before. Like this is just like univariate Lagrange interpolation. Like if I give you I describe a univariate polynomial of degree D by telling you how it should behave at D inputs. There is a linear time algorithm to evaluate the interpolated polynomial at any desired input. So this is just some multivariate analog of that. So anyway, I hope this was a little helpful, but we're about to see an example where you're just directly going to see why the verifier can on its own evaluate the polynomial G that Sumcheck's being applied to very quickly.
Thank you.
Great. Any other questions?
Yeah, maybe just like in the case where we're using like a commitment instead of just oracle, like in place of an oracle, the soundness error is the sum, right, of the soundness error of the Sumcheck and the soundness error of the commitment protocol.
Yeah, that's right. I would just add the following clarification. So the soundness error of Sumcheck itself, if you're running it interactively with no fiat Shamir, is statistical. So regardless of how hard the prover works, it's still going to get caught in a lie with overwhelming probability. With the commitment schemes, like the quote soundness error is coming in. The commitment scheme is like really binding the prover to a fixed polynomial, assuming the prover can't, break, some cryptographic primitive, find a collision in a hash function or something, and that's computational soundness. So if the prover, like the error there is coming in where, if the commitment scheme is configured to 128 bits of security, then if the prover spends 2 to the 60 work trying to break the commitment scheme, it might succeed with some maybe probability 2 to the minus 68 or something. So they're different kinds of soundness error, and you're right, they are kind of additive. Yeah, but I just want to clarify, I guess it's completely statistical soundness error for the Sumcheck protocol until you apply fiat Shamir to make it non-interactive, and then it's computational. Other questions? Cool. Okay. Yeah, so that is the Sumcheck protocol. And in terms of its costs, yeah, so there's one round for each variable of the polynomial. And in applications, again, like if you're dealing with a circuit in a snark, if you're dealing with a circuit of size S, the number of variables will typically be like 2 times log S. Okay, so think of L, that's why I was saying think of L as like 30 or 60 or something. Log S is maybe 30-ish. And so the number of variables will typically be like twice that. And then the degree D is often like two or three. So yeah, there are L rounds, and a degree D univariate polynomial is sent in each round. And so that's, about D field elements in each of the L rounds. So the communication is, D times L. Again, think of it as like maybe 120 field elements total or something. Yeah, the verifier like does very, very simple like checks to process those messages, just evaluating univariate polynomials at like random points. And the polynomials, again, each of them has degree like 2. So that's like very fast, just field operations. And then the verifier also has to evaluate the polynomial being summed at one point. And again, in like snark applications, like the bottleneck is going to be running the evaluation procedure of a polynomial commitment scheme. So that's, the box in the sky here that gives the verifier the evaluation of G will actually be kind of implemented in some way via the polynomial commitment scheme. So that will tend to be the bottleneck for the verifier. Yeah. And then for the prover, I'm going to try to say a little bit more about this shortly, but the short version is, the prover has to at least evaluate G at 2 to the L points, like just to compute the right answer. Okay, in general, anyway. And so we know how to implement the prover in time within a factor, D of that. And again, think of D as like 2. So up to a constant factor, this is like optimal prover time. That's the short version about prover time. I'll try to say a little bit more about the prover time before I'm just totally out of time here. Yeah. Okay, so essentially the verifier's time is dominated by, in practice, evaluating G at a single point, however it has to do that. And the prover time is kind of within a constant factor of like just solving the problem, hiding some intricacies that come up in particular applications, I guess. Okay, so now we're finally going to get to a concrete application of the Sumcheck protocol. So this will make it like much clearer, like why, how you take like a problem people really want to solve in the real world and identify a polynomial G so that like the problem people want to solve in the real world is equivalent to summing up G's evaluations over the Boolean hypercube. Yeah, so it's a problem, that people in like snark land do not care about, but it is a problem people just in the world of algorithms and graph processing and things do care about. It's counting triangles, and this it's just for illustration. So the input here is a graph, so a bunch of if it's think about the Facebook graph, so there are the vertices in the graph are Facebook profiles and edges, any two profiles are connected by an edge if the people are friends with the profiles are friends with each other on Facebook. And yeah, so I'm going to have the input graph specified by the adjacency matrix. So this is a matrix where, there's one row like for every vertex, like every Facebook profile, and one column also for every Facebook profile. And, Aij is 1, like if those two profiles are connected, if they're friends with each other, and it's 0 otherwise. Okay, and counting triangles is just saying, I want to know how many like triples of people in the graph are all friends with each other, right? So Alice, Bob, and Charlie are pairwise, Alice is friends with Bob, who's friends with Charlie, who's friends with Alice. Right, counting triangles is that problem. Like how many 3 clicks are there in the graph? Okay. Any questions about the problem? All right, so the fastest known algorithm for this problem, what it will do is it will like take this adjacency matrix and it will square it. And then once you have that squared adjacency matrix, it's like a linear time, meaning n squared time procedure to count the number of triangles. So that's, so the fastest algorithm runs in like matrix multiplication time, which right now is super linear. It's an open question whether we can actually get a nearly linear time algorithm. All right, so yeah, I'm going to tell you how to use the Sumcheck protocol to get a linear time verifier. So the verifier will be, faster than the fastest known algorithm for this problem, and hence it's a useful protocol, right? The verifier is saving work relative to just solving the problem on its own with the fastest known algorithm. Okay, so we have to do this funny thing of interpreting the input not as like an n by n matrix, but rather as a function over the Boolean hypercube, right? Because we're ultimately going to want to take a multilinear extension polynomial. And the only way we can do that is if we have a function whose domain is the Boolean hypercube. So there's a very natural way to kind of take any, bit vector, any matrix, and interpret it as a function over the Boolean hypercube. So here's a picture. So here's a 4x4 matrix, has 16 entries. And we just interpret it in the natural way as a function over the Boolean hypercube. So we're, as the evaluations of that function. So, we say, oh, well, like the top left entry of the matrix is just the function evaluated at 0, 0, 0, 0. This is the function evaluated at 0, 0, 0, 1, right? And the bottom right is the evaluation at 1, 1, 1, 1. Okay, so this is just like the natural way to interpret. We're just like indexing rows and columns by bit vectors rather than integers. That's all that's happening in this interpretation. Okay. All right, so once we've interpreted the input matrix as a function over the Boolean hypercube, we can take a multilinear extension polynomial of that function. Okay, once we have the multilinear extension polynomial of the input a twiddle, we can take it and kind of use it to define a polynomial g, which is not multilinear. So, so what I'm doing is I'm taking the multilinear extension polynomial a twiddle, right? And I'm evaluating it several times and multiplying the results together. So I have a twiddle, so I'm defining g now as a 3 log n variate polynomial, right? So x, y, and z here each have log n variables. Think of x, y, and z as, if you feed in Boolean values to them, like x is like a label of a vertex in the graph, y is also a label of the vertex in the graph, z is also a label of vertex in the graph. And then I'm evaluating like 3 copies of a twiddle, a twiddle of xy, a twiddle yz, a twiddle of xz, and multiplying them together. Okay, so this is exactly like the acrobatics we have to do to kind of take the input to the verifier and turn it into a polynomial g, such that the thing the verifier wants to compute is obtained by summing g's evaluations over the Boolean hypercube. And moreover, evaluating g at a single point can be done by evaluating the multilinear extension of the input at a handful of points. Okay. So what I've done here is I've specifically defined g so that the number of triangles in the graph is obtained by just summing g's evaluations over the Boolean hypercube. Right. Because if I feed in a Boolean vector to the first copy of a twiddle, I basically get out like aij, where like ij is the same as ab here, right? And then if I feeding in Boolean vectors again, this a twiddle yz is the same as ajk, where again, like the b and c in this sum is the same as the j and k in this sum. Yeah, and similarly for the third copy of a twiddle. Okay, so yeah, so to summarize, in order to count the number of triangles in this graph, we can just apply the Sumcheck protocol to this polynomial g, defined as like the product of 3 copies of the multilinear extension of the input matrix. Right, that's it. That's the whole protocol. Okay, and the verifier's time is dominated by evaluating the polynomial being summed at a random point. And that's equivalent to evaluating a twiddle at 3 points. And remember, a twiddle can be evaluated at any desired point in linear time. Linear in the size of the specification of a twiddle, which is just the input size to the verifier. So each of these three evaluations is linear time. So this is like three, roughly like 3 times, the input size time for the verifier. Any questions about this? All right. So hopefully that gives some sense of why, this like weird protocol that like sums up the evaluations of some multivariate polynomial is actually useful for solving problems people care about. You have to do a little acrobatics to kind of, express the problem you care about, as the, a sum of evaluations of some low degree polynomial G over the Boolean hypercube. You also need that the verifier can evaluate G quickly at a random point. But you get it, way more frequently than you would think. Like, once you see a few of these applications, like, everything looks like a nail to this for this hammer. Okay, if there are no questions, I guess I'll try to wrap up in the next 5 minutes. Does that sound okay, timing wise?
It's fine, Justin. I mean, if you have more time, then we have more time.
Oh, okay. Okay. I do have more time, so I'll just keep going. And, if I run out of time, just please let me know that, there's no issue on my end with saying that. So, okay. So I guess I'm just trying to think. I want to convey a little bit about the prover's computation in these protocols, because right now I've explained that the verifier in this counting triangles thing is linear time, and I've just like asserted that the prover time is close to what it takes to just kind of naively compute the sum in the first place. But I haven't gone into the details of that. I'm just trying to think what order to do things in. Okay, let me try to. So I want to convey 2 things, I guess, for the remainder of the talk. So one is the Sumcheck protocol can achieve efficiency properties, especially for the prover, that there's like no other ways known to achieve those kinds of efficiency properties. So I want to try to convey some of that. And then I also want to say a little bit about how the prover is actually implemented efficiently. But so let me actually start with the first one. I'll try to convey a little bit about why the Sumcheck protocol is unique in certain contexts in terms of the efficiency it achieves. So I want to tell you about a more complicated interactive proof for counting triangles, where the prover is what I call super efficient. So this is like this really special property where I'm not aware of like any other way to achieve this. Okay, so what I mean by this is the prover is going to run the fastest known algorithm to solve the counting triangles problem, and then do just an additive low order amount of extra work to prove that the answer is correct. So it's not even a constant factor extra work. It's a totally low order amount of extra work. Okay. Yeah, this slide's a little busy, but it's very so sorry it's so crowded and dense, but it's almost just redoing the previous protocol that we covered for counting triangles. It's replacing the first 2 terms of the sum, defining the number of triangles in the graph, with a different expression for it, which is just the squared adjacency matrix at a single entry of that, right? So, what's happening is, this is actually how the fastest known algorithm works, is it expresses the number of triangles in the graph not as a sum over n cubed terms, but rather as a sum over n squared terms. But in order to do that, it means like the first product gets replaced with like squared adjacency matrix instead of the adjacency matrix itself. So is that clear? Does anyone have a question about that? Okay, so yeah, I guess this is like looking at the powered graph where like I is connected to J if and only if there's some K that connects that's connected to both I and J, and the number of triangles is you just see like is there a length 1 path between I and J, sorry, length 2 path between I and J. That's what this is capturing, and then this is capturing is there also a length 1 path between I and J, and if so, you have a triangle.
Yes, sorry, maybe, sorry for interrupting, but
Yep.
I guess the element of a squared is the number of length to paths and not just if it exists. it's
Yeah,
the
yeah. Thanks for yeah, and that's actually what you want. Thanks for catching that. I
yeah,
misspoke.
right.
Yeah, thanks. Yeah. Okay. So now we're going to, do what we did before, where we view these both matrices A and A squared, like not as n by n matrices, but as functions whose domain is the Boolean hypercube. And now the thing we're going to apply Sumcheck to is not like a product of like 3 copies of A twiddle, but rather just 1 copy of A squared twiddle. So that is squared adjacency matrix, take the multilinear extension of that, and A twiddle. Yeah. So this expression, like summing this over the Boolean hypercube or over pairs of nodes ij, is equivalent to summing this H over the Boolean hypercube. So all we do is we apply the Sumcheck protocol to this H. Okay. And the key point here, and I am going to try to like just hand wave, but give some idea of how the prover actually works. Once the prover knows A squared, which it has to compute anyway, just in the process of running the fastest known algorithm for counting triangles. The prover can compute all of its messages in the Sumcheck protocol applied to H in just order n squared time, right? So yeah, like the bottleneck for the prover is just determining A squared. And it does not matter how the prover determines A squared. It can use an arbitrarily complicated algorithm to do that. It can, someone can just hand it A squared somehow. As soon as it has A squared in its head, it can apply the Sumcheck protocol to H in order n squared total time. So that's what I mean by an additive low order amount of extra work to prove correctness. So this is where, like, I don't know, like all of, Marlin, Planck, row 16, they would all require the prover to, at a minimum, like cryptographically commit to A squared, which, and these cryptographic commitments, they often involve, I don't know, they're like 3 or 4 orders of magnitude more expensive than just like writing down A squared or something like that. So yeah, I'm not aware of like any other technique, and I would go so far as to say I would suspect there is none. I think you have to go through like an interactive proof and not like an interactive oracle proof or something to get this property of like super efficient prover. Okay, and then so now I'll just say a little bit about what the prover's work looks like to actually compute all of the messages it has to in the Sumcheck protocol, to get this order n squared implementation time. I meant to. It looks like I reversed the order of a couple of slides. So let me just briefly sketch what the prover is going to do, and then I'll show a picture. Okay. So remember, in each round of the Sumcheck protocol, right? Like the prover sends a univariate polynomial, right? Which is if the prover's honest, that polynomial is obtained by sort of leaving exactly one variable of the multivariate thing being summed unbound, right? So like in round I, we've like already sorry, the indices here are messed up because I copied the slide from another talk and forgot that didn't notice that I left these weird indexing. So apologies for that. But hopefully this can still come across. So each round of the Sumcheck protocol like binds another variable to a random field element. So in round I, we've already bound like, most of the variables, the variables 1 up to I-1 to a random field element. We're leaving the I variable unbound, and then we're summing over all possible Boolean assignments to the remaining variables. Okay, so the prover just needs to compute this univariate polynomial, right? And the most convenient way to do this is typically not to directly compute the coefficients of this univariate thing, but rather to just evaluate it at at degree many points. So if this thing has degree 2, I guess you have to evaluate, the prover can just evaluate it at 3 inputs, say 0, 1, and 2. And that's a complete description of the polynomial that needs to be sent. So that amounts to, like fixing the unbound variable xi to like 3 different values, say 0, 1, and 2. And just, computing this annoying sum, with xi fixed to 0, 1, and 2. So that is, in order to compute the honest prover's message in round I, it's enough for it to evaluate the polynomial being summed at points of this form. So, right, we've like bound the first I-1 variables to random field elements. we have to set the ith variable to 3 different points, 0, 1, and 2. And then, we're summing over all Boolean values, like evaluations at points where the remaining variables take, all Boolean values. So that's what's happening in the prover's head, is it's just looking to evaluate the polynomial being summed, h, at all points of this form. Okay. And remember, like in this counting triangles protocol, h it's like a product of let me go back to that. It's a product of a squared twiddle and a twiddle. Right. So whenever you want to evaluate h at a point, it's enough to evaluate a squared twiddle at a point and a twiddle at like the same point. So in its head, the prover is just going to have to be able to obtain like, the evaluations of a squared twiddle and a twiddle at, this list of points that it needs. And again, that list looks like, this is the list of points, right? Like the first I-1 variables are bound to field elements. The ith variable ranges over 0, 1, 2, and the remaining variables range over all Boolean values. So it turns out, oh, sorry, question?
Is it a specific reason why you choose 0, 1, and 2?
No, you can choose any 3 points. You do get some nice simplification and like speed ups for the prover. It turns out by having 0, 1 in there, but yeah. And actually, I go so far as to say, if you really optimize this all the way, you don't even need it to evaluate it at 2, I guess, because to pass the verifier's consistency check, in each round, it checks, like in round 1, remember the verifier checks the claimed answer for the whole problem C1 equal S1 of 0 plus S1 of 1. Okay, and that means as soon as you tell the verifier S1 of 0 and S1 of 1, how do I want to? There's like a unique evaluation for at input 2. I shouldn't. That's 2 in the weeds. I got myself tripped up as I tried to explain it, but yeah. So there's nothing special about 0, 1, and 2. Any 3 points would work, but there are some nice optimizations that come if you at least have 0, 1 in here. Okay. Yeah. So what's happening in the prover's head is it's going like in each round of the Sumcheck protocol, like another variable gets bound to a random field element, and it just needs to be able to like maintain a data structure so it can like quickly evaluate, like a squared twiddle and a twiddle at the points of this form. And so this is what the data structure looks like round by round. So at the start, here I'm just focusing on a squared twiddle. So the same thing would happen with a twiddle. So at the start, like in the prover's head, it's just storing all the entries of a squared, right? That's it. Which again, the prover had to compute a squared in the fastest known algorithm for counting triangles anyway. So this matrix here is just sitting in the prover's head already before the Sumcheck protocol even begins. Right. And then when the first variable gets bound to R1, the verifier picks a field element R1. It turns out like it's enough to kind of take a kind of a certain linear combination of you pair up the entries of the original matrix and take a certain linear combination of each pair of entries with the coefficients of the linear combination determined by R1. And then, so when the next variable gets bound to R2, you pair up, the entries of the data structure again, and take a random linear combination of each pair, where again, the coefficients in the combination are determined by R2. And so this can, it can actually happen like in place in the prover's head, where, kind of just makes a streaming pass over its data structure. And like looks at every 2 elements and takes a linear combination and like kind of overwrites. You can overwrite the data structure each time, and thereby like use kind of 0 extra space if you care about that. Okay, so I'm hand waving and like I'm not telling you exactly how you can go from like the data structure in round I to the evaluations the prover needs in round I, but it's, you can. This is what the whole prover computation looks like. Does this make sense? Any questions? Okay. Yeah. So if people talk about linear time Sumcheck, like this is what they mean, like this procedure happening in the prover's head. And it applies whenever the polynomial that Sumcheck is being applied to is like a product of a small number of polynomials where the verifier is able to obtain like all evaluations of those polynomials over the Boolean hypercube in its head, like at the start of the protocol, like quickly. So in snarks, typically like the polynomial in the prover's head is exactly just the multilinear extension of the witness. And so, just by virtue of knowing the witness for the statement being claimed, the prover like has this data structure in its head already and can then start, running the rounds of the protocol and sort of collapsing the data structure by half each round. Okay. All right. So just to sum up, to finalize the protocol, so there is a detail, an important one that I've brushed under the rug here, which is that at the end of the Sumcheck protocol applied to this polynomial h, right, the verifier does have to evaluate h at a random point, which requires evaluating a squared twiddle and a twiddle at a random point, right? And we know that the verifier can get a twiddle at any point quickly because it's actually handed like all evaluations over the Boolean hypercube of a twiddle. But the verifier does not know a squared. So it cannot get a squared twiddle at a random point on its own quickly. Okay, so what it does is it forces the prover to compute that evaluation for her. And to do that, you have to give an efficient interactive proof for essentially matrix multiplication, right? So now we need an interactive proof that, the verifier is given as input the matrix A, right? And now wants the prover to compute and prove the correctness of a squared twiddle. Okay, and I'll just briefly fly through this fast enough that you might not follow it, but yeah, there's like a special purpose interactive proof you can give like specifically for this problem, and it follows directly basically from the definition of matrix multiplication, which is that the ijth entry of a squared is just the sum over all k of aik times akj, right? That's the definition of matrix multiplication. And which means if I just stick a twiddle over everything, you actually get an equality of formal polynomials. And the way to see this is like both the left-hand side and the right-hand side are multilinear in I and j, right? Because I appears only once on the right-hand side and j appears only once in the right-hand side, and they're getting fed into this multilinear thing, a twiddle. So, the right-hand side is multilinear in I and j. And it agrees with the left-hand side at all Boolean inputs for I and j. So once you have those two things, right, you have two polynomials, the left-hand side here and the right-hand side, and they're both multilinear, and they both take the same values over the Boolean hypercube. You actually know they're the same polynomial because multilinear extensions are unique. Okay, which means that in order to compute a squared twiddle of R1, R2, it's enough to compute the right-hand side here with I fixed to R1 and J fixed to R2, which you can do with the Sumcheck protocol, now applied to a different polynomial, namely this thing G, which is obtained, from what we're summing here, but with I fixed to R1 and J fixed to R2. Okay, and so this is another example where, things start looking like nails once you have the hammer of the Sumcheck protocol. We've managed to just express this evaluation of a squared twiddle as a sum of some G that's low degree, and whereby the verifier can evaluate this G at a random point, because for that it's enough to evaluate a twiddle at two random points, and the verifier is handed all evaluations of a twiddle over the Boolean hypercube, and we have this algorithm that therefore can evaluate a twiddle quickly. Okay, any questions about this? Okay, so I'm just about done what I prepared to cover. So I guess I want to just say two things now. Yeah, so I think we're going to see some applications soon that do achieve like this like super efficiency for the prover that people like actually care about. So this counting triangles protocol, like, you know, in snark world, no one's counting triangles over like committed inputs or something. So who cares that there's a super efficient protocol for counting triangles? But things people do care about are like, one example is a snark for neural network evaluation. And you know, a lot of the neural networks people are training up today, they really do just like matrix multiplication repeatedly, you know, followed by like nonlinear like activations. So the bottleneck really is matrix multiplication in terms of training up that network. And so like a super efficient protocol for matrix multiplication kind of maps directly onto that problem. And so you should be able to get like super efficient snarks for, you know, training up neural networks. And there's like, I know of no other way to do that, where like you kind of just run the training algorithm with no proof of correctness and do a lower amount of extra work to prove correctness. And I think we're going to see some additional applications soon that people actually care about in cryptography. So we'll see, but I am optimistic on that. And then the other thing I want to say, what else do I want to say? Okay, so yeah, there is one other. So I do want to talk about one snark that has a prover is efficiency property that other snarks don't. And this is a general purpose snark. So yeah, I've described like a very special protocol to you for like matrix multiplication and counting triangles. When, you know, what people are using today is like, you know, general purpose snarks, meaning for circuit SAT or other NP complete problems, that they're efficient reductions from computer programs to those problems. So here, I'm now going to tell you about a snark for circuit SAT. And it has a nice efficiency property for the prover that is unique. Although it's not totally clear to me that there are many applications people care about where this unique property is particularly useful. Anyway, this will become clearer in a second. So yeah, there's a very important and nice interactive proof called the GKR protocol. This stands for its, you know, inventors Goldwasser, Kalai, and Rothblum. So this is an interactive proof for circuit evaluation. So to tell you, you know, some background that I'm sure everyone knows. When people use snarks today, I mean, at least the aspirational idea is like someone who maybe knows nothing about snarks will write like a computer program that takes as input the witness that the prover claims to know and checks the witness's validity. So, you know, in the hash preimage example, it'll take as input a hash input X and evaluate the hash function on X and confirm that the result indeed equals the prover's claim Y. And the idea is we would take that computer program and turn it into an equivalent intermediate representation like a circuit or a instance of R1CS or something. And then you'd run a snark for circuit SAT or R1CS or something, whereby the prover proves that it knows a satisfying assignment, you know, for the resulting circuit. And yeah, so the front end, people call it a front end, should take it, you know, take the computer program and like turn it into equivalent circuit. And then the back end is like the snark for circuit SAT that the prover will apply to prove it knows the satisfying assignment to the circuit. Okay, so the GKR protocol is an interactive proof for like evaluating this circuit. And I guess what I want to say is in a snark setting, the input to the circuit will actually be committed with a cryptographic commitment scheme. Okay. Yeah, so, but I want to describe the GKR protocol as an interactive proof, which assumes the verifier actually knows the whole input to the circuit. So it's like a protocol for circuit evaluation, meaning like the verifier knows the input to the circuit, but by combining it with, you know, polynomial commitment schemes in particular, you can actually get a snark whereby the prover will actually commit to the input to the circuit. And at the very end of like the interactive proof, it'll just use the polynomial commitment scheme to kind of reveal the necessary information to the verifier about the committed input for the verifier to run its check in the interactive proof. So let me just, I'm just going to give like a super high level sketch of roughly how the GKR protocol operates. So the prover starts by sending the claimed output of the circuit, right? And then the verifier doesn't believe the claim. So it's in the guts of the GKR protocol, they apply the Sumcheck protocol to a certain polynomial. I'm not going to tell you what the polynomial is. And at the end of that Sumcheck protocol, the verifier has to evaluate that polynomial at a random point. And to do so, it turns out to be like both necessary and sufficient for the verifier to evaluate like the multilinear extension of the preceding layer of the circuit at that point, right? So that's like, very hand-wavy terminology, but what's happening here is, when you evaluate the circuit on the input, right, you go gate by gate through the circuit, and each gate winds up like with the value just by evaluating that gate of the circuit, the prover's claim about the output of the circuit winds up kind of getting reduced to a claim about the values of the gates feeding into the output. And formally, it's that claim is like the multilinear extension of those values at some randomly chosen point equals something. So the verifier can't directly check that claim because it does not know the values of the gates feeding into the output without just like evaluating the whole circuit up until the output gate. So it doesn't stop. It just does the same thing again. So it runs the Sumcheck protocol again to reduce the claim about the gates feeding into the output to a claim about the preceding layer, and it just goes layer by layer through the circuit until eventually the prover makes a claim about the multilinear extension of the input to the circuit. Okay, and in the setting where the verifier actually sees that input, there's a linear time algorithm for the verifier to sort of check that claim directly on its own. Okay, so that's how the GKR protocol works without saying like anything about what polynomials the Sumcheck protocol is actually getting applied to. But the key performance point here is that the cryptography, the polynomial commitment scheme, is only getting applied to the witness to the circuit. So that is like the inputs to the circuit. So for like every other general purpose snark out there, the polynomial commitment scheme like gets applied to the whole circuit, right? So in Marlin or Gross 16 or Planck or whatever, it's like the prover in its head evaluates the whole circuit gate by gate and then interprets the entire like list of gate values as a polynomial and commits to that polynomial. In the GKR protocol, the cryptography works as follows: like everything is just field operations, up until the very end of the interactive proof, when the verifier needs to evaluate the multilinear extension of just the witness at a random point. So that means that the prover is applying like all of that cryptography like just to the witness. In most applications, I think the witness tends to be like only a constant factor smaller than the whole circuit. That's particularly the case when the circuit takes a lot of advice inputs. These efficient reductions from computer programs to circuits tend to only be efficient if there's non-deterministic advice, that kind of help the circuit like do the computation. So that's why I think this GKR protocol derived snarks are not seeing very broad deployment, is like this really nice benefit of cryptography only getting applied to the witness doesn't actually come up all that much. But there is some of this, and there was some work out of Consensus that's looked at using the GKR protocol, snarks from the GKR protocol specifically. And yeah, they like it because everything is field work other than committing to the witness. And I guess in whatever application they're looking at the witness, it really is small. Okay, so that's it. I just, in this talk, I wanted to try to convey these efficiency properties for the prover that I think you really can only get via the Sumcheck protocol. And if anyone's interested, I will, this MOOC lecture, I'm going to talk about like snarks for R1CS and CircuitSat that are much more like comparable to the costs of other snarks. Although I still think there are some efficiency benefits of Sumcheck-based snarks, even the ones that are more comparable to alternatives. Okay, so that was everything I wanted to convey. And yeah, I still have, if anyone wants to ask questions, I'm happy to take them. But yeah, thanks so much for having me again.
Oh, thanks for the amazing lecture. That's really,
Yeah.
So like in the original subject that we discussed, like there's I think I'm sure you've seen those the blog where we wrote about the peer champion, like you need the challenges before you go to the next stage. Right?
Mm-hmm.
So is there any way around this this kind of thing, or because the protocol is designed in this way? There's very little we can do to bypass this getting this peer to measures.
Yeah, I think it's completely unavoidable because I think the whole idea of fiat Shamir is like you're supposed to have no idea like what the next hash value is going to be until you fully computed like the current round's prover message. So I think that issue, yeah, you raised is a real issue. And I guess what is less clear to me is how does that issue compare to like other potential bottlenecks, I guess.
Yeah. It's just like when we try to look at it in similar, compare different purpose together. If there was any way around it, that was the question. That was the.
Yeah. So I don't, I might just lack imagination, but I think there's no way around it. Yeah. That's right. I guess, yeah, I mean, one nice thing is with this data structure, like collapsing each time, it does eventually just like fit in a small amount of memory or whatever. But yeah, and I think another thing I guess I'll mention is you can play around with the degree of the polynomial like sent in each round of Sumcheck and the number of rounds, and thereby get faster shrinkage per round. And so yeah, when we sum over the Boolean hypercube, you're kind of taking an extreme of that trade-off where you're trying to minimize like the total proof size, but that actually maximizes the number of rounds and also like minimizes the round-to-round shrinkage of the data structure. So you could use so basically, like rather than summing over the Boolean hypercube, you could sum over, like rather than 0, 1 to the blah, you could sum over like 0, 1, 2, 3, 4 to the blah. And you'll have the number of rounds, and like in every round, you get a factor 4 shrinkage of the data structure instead of factor 2. But in each round, the polynomial sense will have degree, like 4 or 5, something like that, rather than degree 2. Yeah, so there's probably beneficial trade-offs if this issue in the blog post is a bottleneck. There are things you can, knobs you can still tune to try to lessen that bottleneck, I guess. It'll make the proofs a little bigger. If you don't like that, you could, try snark recursion to make the proofs smaller again. But yeah, I guess it's nice that in Sumcheck the proofs are just field elements. They're not like cryptographic group elements or something. So, they might be, more field elements might be roughly equivalent to fewer group elements. I don't know. Gotta think about the comparisons get all nasty and very hard to do some say, oh, this snark is definitely going to have like a bigger proof than this snark because there are knobs to tune and blah blah blah. Yeah.
So I have maybe a general question. If we're talking about Sumcheck, and Sumcheck is actually maybe a type of application, right? That we're trying to run.
Mm-hmm.
But if the application were different, so it wasn't a Sumcheck, it was maybe a partial Sumcheck, I could technically think of a similar scheme, right? And it seems that at the end of the day, I should always be able to go down to one use of the oracle, right?
Mm-hmm.
So if the application, for example, was maybe sampling some polynomial, some multilinear extension at one point, and that was the application, and not at 2 to the power L points. Then I should be able to do it all in one round, right?
Okay, so this gets a little tricky. So, but I guess I think of Sumcheck, by the way, as like not as an application itself, but as like a hammer that you then, apply to in the applications people actually care about, like, I don't know, a snark for neural network evaluation or whatever, who knows. Yeah, you're depending on the setting, the verifier might or might not be given an explicit description of the polynomial being summed. Okay, and you're right. Like if the verifier is handed this polynomial being and just wants to evaluate like a list of all of its evaluations or whatever, and just wants to evaluate it at a random point, like the linear time algorithm will do that for the verifier on its own, and there's no point in bringing in the prover. But like this like squared adjacency matrix thing is I guess a good concrete example, right? Like within the counting triangles protocol, like the verifier needed to evaluate the extension of the squared adjacency matrix at a random point, but didn't actually know, it was never handed an explicit description of that squared adjacency matrix. That's like computing that is exactly the work it wants to avoid. That's why it's using the prover. So then even that single evaluation is like kind of usefully outsourced to the prover. So yeah, this was, I guess, a roundabout way of saying, like, is whether summing up those 2 to the L evaluations of the polynomial is like easier or easy is harder, strictly harder than evaluating it at a random point or not, like depends on the setting. Like, is the verifier just like given a list of all those evaluations or not? Does that make sense? Maybe not. Didn't make sense. I think you're muted again, but
I'm on mute. No, it's yeah. I think it's something that I still need to think about. I think, but I see your point. Yeah, it may not extend to the same class of applications that Sumcheck extends to, I guess.
Yeah. So yeah. Okay, maybe I'll leave it at that. Yeah, I mean, the discussion, I haven't figured out like kind of the best way to talk about these things, especially when people are seeing Sumcheck protocol for the first time, because like the whole like cleverness in like wielding the Sumcheck hammer is always about like how do you cook up some low degree polynomial so that like summing up its valuations gives you the answer you want, and the verifier can evaluate it efficiently at one point, or if it can't, you can like recursively apply Sumcheck protocol again to offload that one evaluation to the prover. And the fact that like you have to like be clever to identify what the polynomials are, and like only at the very end of all of these applications of Sumcheck, potentially, in the GKR protocol, it's like one application per layer of the circuit. Only at the very end do you finally get an evaluation that the verifier can compute on its own. So you're dealing, you just have all these polynomials that the verifier doesn't even know what they are, and just like keeps making the prover do the evaluation work for it until the very, very, very end, when there's finally a claim about a polynomial the verifier is given explicitly a description of. And then even that description for the verifier is oftentimes implicit, where it's not just a list of all of the evaluations of that polynomial. In the matrix multiplication application, that was the case, but there are some applications where like the polynomial the verifier does evaluate at a random point is actually like maybe described by handing the verifier like a small circuit that takes as input you know, the input you want to evaluate the polynomial at, and spits out the evaluation. So this actually, the very original first application of Sumcheck protocol, which is completely theoretical and not practical, that was the setting. So they were interested in, like, it was computing the number of satisfying assignments to a circuit or formula. And the polynomial Sumcheck was applied to was actually obtained by taking that circuit and, like, turning it into an arithmetic circuit that computes some polynomial that the verifier evaluates at a random point just by, like, going gate by gate through that arithmetic circuit. And that, yeah, to be clear, like, that polynomial being summed is, like, not multilinear at all. It's like, you know, the degree of that polynomial is at potentially, like, the size of the circuit. So yeah, it's like, it gets very weird in different applications, like how the polynomial handed to the verifier is actually specified to let the verifier evaluate it at one point. Okay, thanks for letting me, like, ramble and babble for so long. Very patient crowd, yeah.
Just one last question from me, and then I will stop. So it's in the GKR protocol, the communication complexity is proportional to the depth of the circuit. Right. So okay, so it should be used for our problems which have a low depth circuit.
Yeah, that's right, and I can say a little bit about that. So in general, this was another, I should have mentioned this, but another reason people, I think, don't like to use the GKR protocol unless the witness is, like, really small, so you really get a prover benefit, is the proofs will, like, always be bigger than other snarks. I mean, the question is how much bigger. So one thing to point out is, like, once you allow non-deterministic advice for the circuit, which, like, you know, all of our efficient, like, front ends, they in general use non-deterministic advice to keep the circuit small. Small depth is actually, like, universal, right? So you can take any computer program running in time t and turn it into a circuit of depth like log t and size like close to t. And so like, small depth is universal, but those techniques use a lot of advice. So you'll get a small depth circuit, but, like, one with a very big witness. And then it's like, okay, well, if the witness is so big, like, there's really no benefit to the GKR protocol anyway. Yeah, so that's why I'm not, like, telling people, oh, you should definitely use the GKR protocol, right? There are very limited settings where the witness is small, the depth is small, but small depth is universal if you allow a big witness. So yeah. Does that make sense?
Cool. Yeah.
Okay.
Okay.
Yeah. So yeah, you're right.
Justin, thanks for coming and talking to us. It was really, I mean, I enjoyed it, and
yeah, I'm happy to hear that. I'm very happy to talk. And yeah, if you want to schedule any follow-ups, it sounds good to me.
Yeah, we definitely will. Will. We'll hold you up for it.
Okay, sounds good.
Okay. All right.
All right. Have a good one. Thanks again.
Yeah, bye.